Hello friends. So today we are going to discuss a total of 4 questions. Rather we can say 5. So these are from the year 2004. So there are 2 questions based on 2004. And then we have 1998. And we have 1996. And we have 1982. Yes, we are going to discuss all these questions. So in the first one, we have from the year 1982, and in this question, it is asked that 3 identical closed coils A, B and C are placed with their planes parallel to one another. Coil A and C carry equal currents as shown in figure. Coils B and C are fixed in position and coil A is moved towards B with a uniform motion. Is there any induced current in B? If no, give reasons. If yes, mark the direction of the induced current in the diagram. So we have a total of 3 discs A, B and C, and the only disc A and disc C are carrying the current, and the position of this B and C is fixed. And the current in A and B is also said to be equal. Okay. And we are only interested in the induced current in B. So, first of all, it is given that we have B and C. These are fixed and A is moving towards B with uniform motion, and A and C, they carry equal current. Equal current and direction is also same. Equal current and we can say same direction. So we are only interested in coil B. So let us first of all see the effect of coil C on coil B. Effect of coil C on coil B. Here effect of coil means basically effect of the current and the motion of their respective coils. So we are given that B and C are stationary. So it means the magnetic field produced by C remains constant with respect to B, because C is carrying current. So we can say the magnetic field produced by C remains constant with respect to B. So we can say the magnetic flux due to C let us write it as phi on coil B because of C, and that will be equal to magnetic field of C and area of coil B. So in this case, BC, this is magnetic field due to coil C, magnetic field due to coil C, and we have AB is our area of coil B. Area of coil B. Now since B and C are fixed, so therefore the flux through B due to C does not change by over time. So we have given that B and C are fixed, the flux through B due to C does not change over time. So we can say that the change of flux on coil B because of C is equal to 0. And because of this, the induced EMF which we can say E B comma C, which is our minus d phi by dt will be equal to 0. So as the induced EMF is equal to 0, so from here we can draw a conclusion that no induced current in B due to C. No induced current in B due to C. Now we come to the coil A and coil B. Effect of coil A on coil B. So we can say magnetic field due to A at B. Magnetic field due to A at B. Let us call that BA, which will be equal to mu naught I upon 2R. And for the sake of simplicity, we assume that the distance between these two coils is given as R. So here R is distance between A and B. Distance between A and B. Now it is also mentioned that coil A moves towards B. Moves towards B. So therefore this distance R will be decreasing. So you can say the distance R is decreasing, or we can say the magnetic field BA is changing over time. BA is changing over time. So we can write that a flux through B due to A. Flux through B due to A, we can write as a phi flux through B due to A will be equal to magnetic field because of A, and we have area of B. From here we can calculate or find out the induced EMF. You can say induced EMF in B due to A, and we can A, B comma A, which will be equal to minus d phi B upon dt. We substitute the phi B A, and we get induced EMF at B because of A will be equal to minus A, and this becomes a derivative of magnetic field of A with respect to time. Now we substitute, or we can say we can just make a little adjustment in this formula. We can write this as dB upon dr and dr upon dt, and dr upon dt is nothing but our velocity, and you can say that this will be equal to minus of A dB upon dr, and here we have say negative velocity, and this can be further written as this comes AV dB upon dr. So we can say that the EMF is not equal to 0. So because of this, EBA is not equal to 0. So you can say a current is induced in coil B because of A. Current is induced in coil B due to coil A. Now we know that the current will be induced, but now we are going to find out its direction, and the direction is based on the Lenz's law. Okay, so you can say Lenz's law, which states that this induced current must oppose the increase in flux, because the coil A is moving towards coil B, so the flux that being associated with coil B is increasing continuously, and Lenz's law states that the induced current must oppose this increase in the flux. Induced current must oppose the increase in flux. Increase in flux. Therefore, and the direction of current A is clockwise. You can see A is current direction is clockwise. So producing a magnetic field into the plane of B, into the plane of B. Now the induced current should be such that the magnetic field that is being generated by B must be in the outward direction. So we can say to oppose this, B must generate an outward field. So you can say corresponding to anti-clockwise induced current. Corresponding to anti-clockwise induced current in B. So the direction is our anti-clockwise, and only this coil A will be able to produce the magnetic field. Now in the next question, it is given that a solenoid has inductance of 10 Henry and a resistance of 2 ohm. It is connected to 10 volt battery. How long will it take for the magnetic energy to reach 1/4 of the maximum value? Okay. So we are given that we have inductor of 10 mH and a resistance. Okay, so we can draw approximate diagram. So we have inductor and a resistance, and this is connected to a 10 volt battery. So this is our L and R, and we have battery of 10 volt. So this is the basic figure. We have inductor and resistance, and value of inductor is given as 10 Henry and resistance is given as 2 ohm. And we have to find out how long will it take for the magnetic energy to reach to its maximum value. Okay, so energy will be only stored in the inductor. So we can say that energy stored by the inductor let us suppose that given U will be equal to half Li square, and we are going to find out the maximum current because we are interested in the maximum value of this energy. So we can say maximum current, let us suppose we call it I max, and this maximum current will be only when the entire circuit had reached the steady state condition. So you can say at steady state, which basically means that t tends to infinity, current reaches its maximum value. And in steady state, we also know that our inductor will act as a short circuit. So now the current will be only dependent upon the resistance. So we can say our maximum value of the current I max will be equal to V upon R. V is given as 10, resistance is 2 ohm. So we get this maximum current is 5 ampere. So therefore, the maximum magnetic energy stored in inductor stored, if given as Umax, will be equal to half Li square and its maximum value. And we already know this is half, inductor is 10, I max is 5 and its square, which will be coming as 125 joules. And we need to find out when energy reaches 1/4 of its maximum value. So we need to find the time, find the time when energy reaches 1/4 of its maximum value. So we want that our energy should be equal to 1/4 of maximum value, which comes as 125 divided by 4, which will be equal to our 31.25 joules. And we are going to find out the value of the, or we can say we are going to find out the time. And we have this LR circuit, and for LR circuit we already know the equation which defines the current as a function of time. So we can say current as a function of time, and that equation is our I of t is equal to our I max 1 minus E minus t upon tau, where this tau is our time constant. Tau is time constant and is given as L upon R, which is 10 upon 2, and this is our 5 seconds. And at any time t, if the energy stored in the inductor is half Li square, so we say that energy stored in inductor at time t, let us call that as U of t is half Li square. And we are already asked that this, we have to find out the time when the energy is 1/4 of the maximum energy. Okay, so we substitute it, and this gives us our half Li square is equal to 1/4 of maximum value of the current. And so from here one second, yeah, let me correct it. So we can say that our half Li square will be equal to 1/4 and multiply with the maximum energy, and the maximum energy is given as half Li square and its maximum value. And this half L and half L cancels out. So from here we can find out that our I will be equal to I max divided by 2. So we get I max we already know. So we get I will be equal to 5/2, which comes as 2.5 amperes. So we already know the value of the current at any time t, and we know the maximum value. We put in this equation and we get the time. So we can say, let us call this equation number 1. From equation 1, we have 2.5 is equal to 5, 1 minus e, and this becomes t upon tau. Tau is about 5. Now it is simple calculation. So we can write our 1 minus e minus t upon 5 is equal to 2.515. Excuse me. 1 minus e minus t upon 5 is equal to, this will be coming as 0.5, which gives us e, sorry, this is a minus here, minus t upon tau is equal to minus 0.5, and here minus and minus cancels out, and we get this as minus t upon tau is equal to natural log of 0.5. This can be further written as t is equal to minus tau natural log of 0.5, and we already know tau is our 5, so we get this as t is equal to, and this natural log of 0.5 is approximately 0.693. So we get this as, this is minus, so we get this as 5 multiplied by minus 0.693. This gives that our t is close to 3.47 seconds. So this was asked in the question. In the next question, we have an inductor of inductance 2.2 millihenry is connected across a charged capacitor of capacitance 5 microfarad. The resulting LC circuit is set oscillating at a natural frequency. Let Q denote the instantaneous charge on the capacitor and I the current in the circuit. It is found that the maximum value of the current Q is 200 microcoulomb, and based on this we have these 4 questions. In the first question, it is asked that when Q is 100 microcoulomb, the value, or we can say magnitude of di upon dt. When Q is 200 microcoulomb, what is the value of I? Find the maximum value of I. And when I is equal to 1/2 of its maximum value, what is the value of Q? Okay, only magnitude. And this was asked in the year 1998. So we are given that it is a LC circuit, so we can just draw its approximate diagram. This is our inductor and we have a capacitor, and inductor is given as 2 millihenry, capacitance is given as 5 microfarad. Okay. And they are oscillating at its natural frequency. So the natural frequency will be our omega, and omega will be equal to square root of LC. So if you substitute the values, this comes as 1 upon, let me solve it here. So we can say that we have, okay, now in this case there is One is inductor and another is capacitor. So there will be continuous oscillations between charge as well as current. Okay. You can say that in an LC circuit, the charge and current oscillate sinusoidally. And we can write this equation. Our charge Q will be equal to maximum charge Q max and cos of omega t. And similarly, we can write the value of current, which will be equal to minus omega, which is nothing but derivative of this charge, and this comes as Q max, and we have here sine of omega t. And please keep in mind that Q max is given to us as 200 microcoulomb, which is the maximum charge on the capacitor. 200 microcoulomb. And it is also said that it is oscillating in natural frequency. So we can find out the natural frequency, that is our omega, which is natural frequency, which will be equal to 1 upon square root of LC. We substitute the value. Inductor is our 2 millihenry, so this becomes 2 into 10 to the minus 3, and 5 microcoulomb farad, 10 to the minus 6, and its square root. So we get our omega will be equal to 10 to the power 4 radian per second. So this is the value of the natural frequency. So we start with part A. In part A, we are supposed to find out di upon dt, only magnitude. So find di upon dt when the charge is 100 microcoulomb. And we can use KVL in this LC circuit. We can say, using Kirchhoff voltage law in the LC circuit, and which gives us that L di upon dt will equal to minus Q upon C. So from here we can say that our di upon dt will be equal to minus Q upon LC. We substitute the values of Q, inductor and capacitor. So we get di upon dt minus charge is given as 1000 microcoulomb, inductor is our 2 millihenry, and capacitance is 5 microfarad. So we get this as minus 10 raised to the power 4 ampere per second. But we are only asked the magnitude. So we can say di upon dt, its magnitude will be equal to 10 to the power 4 amperes per second. So this was part A. Now we come to part B. It is asked that find I when Q is 200 coulomb. Please keep in mind that Q is the maximum, this 200 microcoulomb is the maximum charge. Okay. So we come to part B. So this was part A. And we come to part B, and it is asked that find I when Q is our 200 microcoulomb, and the 200 microcoulomb is nothing but the maximum charge. Okay. So we can see at Q is equal to Q max, I is equal to minus omega Q max, and we have sine omega t. And since Q is equal to Q max, and we also know the equation of the charge, Q is equal to Q max cos of omega t, and so which means that for Q is equal to Q max, this cos of omega t will be equal to 1 under the condition when Q is equal to Q max. Excuse me. And which also mean that sine omega t will be equal to 0. And if sine omega t is equal to 0, then let us call this as equation number 2. We can say from equation 2, the value of the current will be equal to 0 amperes. Now we come to the C part, and in part C we have to ask that find maximum value of I. Now maximum current occurs when Q is equal to 0. You can say from here the maximum current occurs when Q is equal to 0, or so this implies that our cos of omega t is equal to 0, or from here we can say that sine of omega t will be either equal to plus minus 1. Therefore, we can say that our I max will be equal to W multiplied by Q max. We substitute the values, we get our I max, omega we, sorry, it is not W but omega. Omega we already know it 10 to the power 4, and Q max we calculated, Q max is given to us is 200 microcoulomb, and this gives us maximum current is 2 amperes. Okay. Now we have to find out the charge in part D when I is equal to I max by 2. I think this was the fourth one. Yeah. We have to find out the charge, its magnitude, when I is equal to half of its maximum value. So we have now part D, and it says that find Q, its magnitude when current I is half of its maximum value. And we already know the equation for the current. We are given that our I is equal to minus omega Q max sine omega t, and I is half of the I max, so we can write this as I max divided by 2 is equal to minus omega Q max and sine of omega t. We substitute the respective values. I max is about 2, so 2 upon 2 is equal to, we have here, because we only need the magnitude, so we just ignore the sign, 10 to the power 4, and this is about 200 10 to the power minus 6, and sine of omega t, and this gives us that sine of omega t will be equal to 1 by 2, and from this we can write that our omega t is either equal to 30 or is equal to 150. Therefore, we get our q is equal to q max cos of 30, which gives us our 200 square root of 3 divided by 2, and if we cancel it, this goes by 100, so we get our charge is equal to 100 square root of 3 microcoulomb. So this was the charge when the current is our half of the maximum value. Okay. And now we come to the next question, which was asked in the year 2004, and here it is asked that in a LR series circuit, a sinusoidal voltage V given as V0 sin omega t is applied. It is given that L is 35 millihenry, R is 11 ohm, VRMS is 220 volt, omega upon 2 pi is 50 hertz, and pi is 22 by 7. Find the amplitude of current in the steady state and obtain the phase difference between the current and voltage. Also plot the variation of current for one cycle on the given graph. In this case, we are given series LR circuit, so we can just draw its approximate diagram. So we have inductor and we have resistance, and it is connected with a voltage source whose equation is given as V is equal to V0, and we have sine of omega t. Value of inductor is 35 millihenry and resistance is given as 11 ohm. And separately, we are also given that the RMS value of the voltage is 220 volt. So first of all, let's find out the angular frequency. Let's find out the omega. Angular frequency omega will be equal to 2 pi f. So this comes as 2. Pi is said to be taken as 22 by 7 and f is given as 50. So we can say our omega will be equal to 2200 divided by 7 radian per second. So this is the value of omega. Next, we are going to find out the impedance of this LR circuit. So we can say impedance calculation. And LR circuit, if the impedance is suppose given as Z, which will be equal to square root of R square plus XL square, and XL is nothing but omega L. And we can find out omega L. XL is equal to omega L, which will be equal to 2200 by 7 multiplied by omega, multiplied with inductor, which is given as 35 millihenry, and this comes as 11 ohm. And we already know value of resistance, so you can say our Z will be equal to 11 square plus 11 square into square root, which will be coming as square root of 242. And this Z, approximately will be equal to 15.56 ohms. Now we are going to find out the, you can say, the peak, we are going to find the peak current, and for that we are going to use the RMS voltage. From that we are going to find a peak voltage, giving us a peak value of the current. So you can say the peak voltage, RMS voltage given, so peak voltage is our V0, which will be equal to square root of 2, and here we have VRMS, so square root of 2 into 220, and from here we get the peak voltage V0 will be approximately equal to 300 volt. Now we can find out the peak current. Peak current, which is our I0, will be equal to peak voltage divided by the impedance. Peak voltage is 311, and this comes at 15.56. So peak value of the current will be approximately equal to 20 amperes. Now we know the I0, we know the V0, we also know our XL, and we also know the value of resistance. So we are going to find out now the phase difference between voltage and current. Phase difference between voltage and current. And if phase difference is represented as phi, so we know the formula that tangent of phi is equal to XL upon R. So this comes 11 upon 11, which is equal to 1. So this gives us that value of phi is our 45 degree. So it means the current, because it is a series RL circuit having an inductor, so the current lags the voltage by 45 degree. So you can say the circuit has an inductor therefore the current lags voltage by 45 degree, and we are supposed to plot for one cycle, and so therefore we can write the equation for the current. We can say our current of I of t is equal to I0, and this comes of sine omega t minus phi, and we are supposed to do it for one complete cycle. So we can say for one full cycle, our t is equal to 1 upon f. So this gives us 1 upon 50 and giving us 0.02 seconds. And this current waveform will be the sinusoidal nature. Only difference is that it is going to have a 45 degree of the phase difference. So we can draw this approximate diagram. We are already given the voltage, so let us draw first of all the voltage, and we have this as 0, and this is our point is given as t by 8, and sorry, it is given as t by 2. not T by 8. So we have this as T by 8, and the last value is given as T. This is given as T. Okay. And we can just make a lag of 45 degree, and so approximately it is going to start from here and producing a lag of 45 degree and going like this. So this point will be over T by 8, this point will be over 5T by 8, and this is our time axis, and this is our voltage and current. So this is our current, which we found the equation as I is equal to 20 sine of omega t minus pi by 4, and the voltage of the equation, this it is already given to us. This is our voltage, and the voltage is given to us as V naught is equal to sine, V is equal to V naught sine omega t. So we have V is equal to V naught sine omega t. And we come to the next question. And this question was asked in the year 2004. And here it is said that in the circuit A and B are the two cells of same EMF E but different internal resistances R1 and R2, where R1 is greater than R2 respectively. Find the value of R such that potential difference across the terminals of cell A is 0 a long time after the K key is pressed. So we have this as a basic circuit to given to us, which is having an inductor as well as capacitor both on parallel, and we have a resistor network having each of value R. Two cells A and B each having a resistance, internal resistance R1 and R2 given, and we have a K key given as K, and we have to find out that the value of R, because they have all same values, so we have to find the value of R such that the potential difference across this A cell is equal to 0. And it is said that after a long time. So long time basically means that we have to discuss the entire thing based on steady state. Condition. Okay. So under steady state condition, we have that the inductor will be acting as short circuit. Inductor will be acting as a short circuit, and capacitor will be acting as a open circuit. Capacitor will be acting as a open circuit. So now as both this inductor and capacitor are parallel to each other, so one end will be the open and other end will be the short circuit. So now we can draw the approximate figure of this. So we have two cells A and B, and we have resistance network and this resistance network consists of two parallel resistances, and they are connected with resistance which are in series. And here now the inductor will be short circuit and the capacitor will be open circuit. So this is our basic circuit. Now we can find out the net resistance. Here each resistance is of R ohm. So we can find out the net equivalent resistance of this particular network. So we have two resistances. So this combination will be giving us R by 2, and here also we are going to get R by 2, and this R by 2 is series with this R, and this also series with R, and both now will be coming as a in parallel resistances. So we can say that our R equivalent will be equal to, these two will be same, so this comes half of R by 2 plus R, and this comes as 2, 3, and this comes as 3R by 4. Now if I is the total current in the circuit, so if you say I is the total current in the circuit, then current through the battery if it is given as I, so we can use Ohm's law, and both these batteries are a cell are having same EMF, that is E. Internal resistance is R1 and R2. So we can write that our I is equal to 2 times E divided by 3R by 4 plus R1 plus R2. Now we are given that the potential difference across the terminal A or cell A is equal to 0, because based on this we are going to find out the value. You can say that given that potential difference across the terminal of A, cell A rather, cell A is 0. So if we use KVL, by KVL we can see E minus I multiplied by R1 is equal to 0. Now we substitute in this equation the value of equation for I, and we can write that E minus 2 times E divided by 3R by 4 plus R1 plus R2 multiplied by R1 is equal to 0. And if we take E as common, we can write this as E, and here you get a 1 minus 2R1 divided by 3 by 4 R1 plus R2 is equal to 0. Now the EMF cannot be equal to 0, So it means the second part of the equation will be equal to 0. So we can write this as 1 minus 2r1 divided by 3, 4 plus r1 plus r2 is equal to 0, which can be further written as 3 by 4r plus r1 plus r2 minus 2r1 is equal to 0. And we can write this as 3 by 4r is equal to r1, and 2r1 will be giving us minus r1, so this comes as r1 minus of r2, and from here we can say our r is equal to 4 by 3 r1 minus r2, so which we were supposed to find out. We are going to find out value of r such that the potential difference between the terminal between the cell is 0. So we found out the value of r. So these were the questions. I think everything is done. Yeah, so these were the questions which was asked in the year 2004, 1998, 1996 and 1982. So these complete all the questions. Thank you.